All right. So chapter 33, number 12, and we'll start here, write down the time. Okay, good. So let's run through this one here. So chapter, what would I do with those? Here we go. So chapter 33, let me make sure I'm in the right one. Good. And then number 12, let me scroll down here. All right. So number 12 says, for what frequency does a 22 microfarad capacitor have a reactance that is below 175 ohms? All right. Well, let me start with the equation and say something that I said at the beginning part of our session 1, and that is capacitors block current or oppose current in a little different way than resistors. Capacitors, as you know, so here's a capacitor. If you build it up with charge, make an electric field inside of it, and that electric field opposes the current. And so when you first have a capacitor, let me just make kind of a switch here, the battery. When you first close the switch, if you remember way back with our capacitors, so I guess it's chapter 28, we said at first, you can treat the capacitor as a short circuit, as a wire, because there is no opposing it. There is no back EMF, if you will. That's because it hasn't had time for charge to build up. And then after a while, it does. And so when you have the AC circuit, so if we get rid of our DC circuit and replace it with an AC circuit, you will have this capacitor partly filling up and then discharging, and then partly filling up and discharging as the current goes one way and then the other. And how much it opposes the current is going to be dependent on the frequency. So you can see for high frequencies, and so if I say omega equals high, then X sub C would be something like 1 over big, and 1 over big would be small. So we are saying basically that for high frequencies, there is very little opposition, very little reactance. And so we like to use the word reactance instead of resistance. So there's very little reactance when you have these high frequencies. So when it says here, for what frequencies does this 22 microfarad capacitor have where the reactance is below? That tells me that for a certain frequency and everything above it, it would be below. So this one, there's going to be some minimum frequency. And then every frequency above that will mean that the reactance is below the 175 ohms. So if I put that into math equations, it says this. It says, when does the reactance less than 175 ohms? And the equation for the reactance of a capacitor is 1 over omega C. And if I replace omega with 2 pi f, and then I rearrange with the 2 pi C, and I'll move the 175 ohms over to there, while at the same time moving the F. You'll see I'm going to get an equation that says when F is greater than this number. So if I grab a calculator, and I'll just do the denominator here, 2 times pi times C, which is 22 microfarad, times 175. And then the reciprocal of that, feel like pretty low number, a little bothered by it. But I got 41.0. I feel like below 175, 2 pi, 22 micro times 175. Get this, take the reciprocal. Okay. So for any frequency greater than, and that actually comes out to be the unit of hertz, and I'll definitely check that, but I'm so bothered by this number. I'm going to go back to the answer sheet. Okay. I did not expect it to be that low, but that's the same as the answer sheet got, 41.3. And just my own personal experience, I guess, because, well, I guess it's 175. I go, because usually, I mean, when I do this for actually building things, we're in the kilohertz. But then again, we're also talking about kilo ohms. So maybe that's the difference. Okay. So anyways, that agrees. But I should also check the units here. Let's do the units. The units would be 1 over. And remember that the unit for a capacitor is a farad. So I have a farad times an ohm. Now, remember that the definition of a capacitance is charge per volt. So maybe right here for the farad, I'll put a coulomb per volt. Now, remember that an ohm, and maybe I should write it as what a resistance is, voltage over the current. So this would be a V over an amp. Coulomb per volt. I feel like I got this backwards somewhere. Okay, so I got a farad and an ohm. Oh, yeah. So the ohm, sorry. So the ohm would be a volt over an amp, much better. That's what I got back. Okay, because I was thinking the volt should cancel. Good. What else do we have? Oh, good. So then the amp is a coulomb per second with a coulomb. And so the coulombs cancel off. And we're just left with per second, which is the whole idea of a hertz. So the units do come out to be hertz, but it's probably nice to prove that the first time. So page 1, page 2. All right, so that's A. And then part B says, what is the reactance of a 44 microfarad capacitor over this same frequency range? Well, we could actually run the numbers, but it might be better just to look at the mathematical pattern here. Remember that this is the idea of the reactance. And we're saying back here that at 41.3 hertz and above, but at 41.3 hertz, the reactance would be 175 ohms. And for anything greater than that, it would be less than 175. Okay, so if you were to double the capacitance, and that's what we essentially did, we we calculated this number based upon 22 microfarads in A, and B is just having us double it. So if you double the capacitance, so if you replace this with 2C, you are going to replace the original reactance with half the value. So 175 cut in half is what, 67 and a half? 80. It goes into 80, yeah, 87. All right, so 87 and a half ohms. So at this 41.3. So we would have 87.5 down to, I guess, 0 as we went to higher and higher frequencies. And that's the range. It says, what is the reactance of a 44 capacitor over this same range? So it would be from 87.5 on down. And let's see the answer. Yeah, so they write it this way, that the reactance would be less than or equal to 87.5 ohms. Good. All right, so that's how I would do, I guess, the first one on your list, number 12. Why don't I go to number 19, chapter 33, and put down here number 19, put down a time so I can make the video a little more clear, or put a timestamp to it to help people out. All right, so let's see, what does 19 say? 19 says, a series AC circuit contains the following components. So why don't I start drawing it? But they said it was an AC circuit. Makes sense. That's what this chapter is all about. I'll make a little AC symbol. And it says it's series, okay. So the following component, 150 ohm resistor. So I'll put a resistor in here first, 150 ohms. An inductor. That is 250 millihenries. A capacitor of 2 microfarad, and a source that has a voltage, and since it's AC, it changes. So we need to say, you know, is this the maximum value, or is this the RMS value? Is it the average value? And we'll probably never say it's average value, because average value is kind of useless. It's 0 no matter what the maximum is. So average doesn't help us much. But the maximum or the RMS does. They're equivalent. So what one tells us, the other one tells us the same thing. Operating at a frequency of 50 hertz. All right, so there's kind of the circuit diagram for those words. Then A says, what is the inductive reaction? Now let me pause right here in case you missed all of this, but all three of these elements oppose the current. Resistors do it by resistance, but capacitors and inductors do it by an electric field. Now, they are different in the sense that the capacitor's electric field is created by charges that build up on the plates of the capacitor. But the electric field that is in an inductor is the result of a changing magnetic field, which comes from the current itself. So that's why it's called the self-inductance. So there is, again, a field, It is an electric field, but it comes from something a little bit different than the capacitor. And so hopefully the two big lessons you'll get by the end of this semester, and maybe even before you go off to Thanksgiving, in case anybody asked, you can say, hey, yeah, Grandma, I learned at school that there are two ways to make an electric field. One is by charges, and the other is by a changing magnetic field. And so that's how I kind of like to describe what happens in our inductors and our capacitors. Both oppose the current. The current is affected by electric fields because they are charges. So anything that creates an electric field would have an opposition or a help, depending on which way the field is pointing. So that's why we call these reactance and this resistance, because they affect or oppose the current for slightly different reasons. And since the inductor comes from Faraday's law, it's related to how fast it's changing. So we expect the frequency in the numerator, whereas the reactance of the capacitor is affected by the charge building up. So we expect an inverse to the frequency effect there, giving the capacitor some time to build up. So the lower the frequency, the more the reactance is. In fact, I'll use that as a springboard to say, maybe we should answer this by doing A and B at the same time, because the reactance of the inductor is omega L. The reactance of the capacitor is 1 over omega C. So there it is. They both have to do with frequency, but the frequency is in the numerator in the inductor because it has to do with the rate of change. It's Faraday's law. But the reactance of the capacitor is in the denominator because, again, the reactance has to do with the charge that builds up, and the charge that builds up needs time. So it would be inversely proportional to the frequency. So it would be proportional to the period, So the period is inversely proportional to the frequency. So now we can just multiply these together, starting with the inductor. Omega would be 2 times pi times 50 times the L. What I say the L was 250 millis. So I'm going to write it as 0.250. And that comes out to be 78.5. Now, again, maybe it's worth going through the units a first time to make sure that that comes out to be ohms. But again, it kind of plays the same role as resistance, but it's a little different effect. So that's why we like to use the word reactance. If I look at the units here, and I'll just put the units down here on this line, but the 2 pi f, that's a hertz, okay, the unit of frequency. And then the inductance is in henries. Now a hertz is 1 over S. Now a henry, always a hard one to remember. So let me show you a good way, I think, to remember it. It says the EMF is minus L di dt, which if you rearrange it means that L is the magnitude of the EMF. So I'll get rid of the negative, divided by di dt. So the meaning of a henry is that you would get 1 volt when the current was changing at 1 amp per second. So the seconds would cancel off and you would have volts over an amp. And a volt over an amp is the definition of an ohm when we did Ohm's law. So yes, it does come out to be ohms. All right, now the reactance of the capacitor would again be, and I'll just kind of go through the same math. Put down here for omega, I'll put a 2 times a pi times a 50, and then times the capacitor, which would be a 2 microfarads. And so that's the denominator. Take the reciprocal of that, and I get 1,591. Oh, not over. Already did the over. 1,591 ohms. And I guess I would have to say that in this circuit, the biggest thing opposing the current is the capacitor. The resistor is at 150 ohms. That's actually more than the inductor. But the big thing that's opposing it is the capacitor. You might argue that for this particular circuit, these particular numbers, we would say we're kind of on the low side of the frequency. So 50 is on the low side because we're giving, at 50, we're giving plenty of time for the capacitor to build up its charge and therefore create a field inside of it. And this one, the inductor, we're really barely changing it. We're only changing back and forth 50 times a second. So this has very little opposition, only 78. The resistor is kind of the same no matter what. It's just got a certain amount of friction, if you will, 150. But even the two of them together, the resistor and the inductor, don't even add up to as much as the opposition coming from the capacitor. So we would say that this circuit is operating in its low frequency range, and for whatever reason, whatever the design criteria is, that could be a good thing or a bad thing, but it's definitely more affected by the capacitor. In fact, you could take the inductor out and pretty much have the same effect. I mean, it does have a little effect. It's 78, but by the time you take 1,591 and maybe even add the resistor of 150. The extra 78 from the inductor is kind of minor. So I would say probably for a circuit like this, unless we're changing the frequency, this inductor is not doing anything. At this particular frequency, it's kind of useless. It's just a waste of a space on our circuit board. It's a waste of money putting the inductor there. Not needed here. Like I said, that's if it stays at this frequency. I haven't read the rest of the problem, so I don't want to completely say that the inductor is being useless here, but the main role is definitely being played by the capacitor. Now, I should also check the units here. Let's see, 1 over, and again, frequency, so that'd be in hertz, and capacitance would be in farads. So now remember, a hertz is 1 over a second. So I'll just take the reciprocal and put the seconds up above. And I should have done square brackets. That's kind of the universal symbol for telling people we're dealing with the units on this step. We're not dealing with the numbers. Okay, so my reciprocal of hertz would be a second. Now, a farad is a little bit easier to remember than the Henry, but the capacitance is the charge per volt. So it would be the coulombs per volt. So let me put coulombs per volt here. Now, again, dealing with the unit, let me put seconds here. A volt could be thought of as an amp times an ohm. And I'll just leave the coulombs down below. And then remember, this amp is a coulomb per second. So this amp, which is a coulomb per second, would cancel with this coulomb and that per second with that second and be left with just ohms. So sure enough, just as a little proof to you, this does come out to be units of ohms also. So there is the A and B. What is the reactance of each of these? Now, there's more to this problem, I think a lot more. C says, what is the impedance? Okay, now, the impedance is a fancy word for saying, okay, what is the total overall opposition? I mean, some of it comes from the inductor, some of it comes from the capacitor, and some of it comes from the resistor. And it gets kind of complicated because you can't just simply add them together, because you have an opposition, but it changes with time, and it changes in time at a different phase than the capacitor and the resistor. And so that's why I guess I kind of solved the differential equation to show you that the current is kind of at a different phase for the inductor. That's why we use the word Eli for the inductor and the word ice for the capacitor. And so it turns out that they tend to be the equivalent of being at right angles to each other. And so we said we got to add them in quadrature. So the overall effect, the impedance, was to say that the reactance from the inductor and capacitor are actually battling each other. They're opposite in phase. So instead of adding them together, you would subtract them. And then the resistance also comes into play. But it comes into play like you would be adding a vector at right angles, because one would be like a sine function and one would be a cosine function. So to get its magnitude, we have to add it like we would do a Pythagorean's theorem, a quadrature. We call that addition and quadrature. So I'm going to combine them together, but I'm going to combine them in a way that is not just simply adding them. And that's probably the hardest thing in this chapter, is to realize that, hey, if I just had three resistors, if I wanted to know the overall resistance, I would just add them together. And we proved that back in, I guess that would be chapter 27 and 28. But something that is an AC circuit, is more complicated. So when they're in series like this, you combined them, is a better word than say add them, because you've got to combine them and combine them with the phase that they're behaving. And so again, the inductor capacitors are opposite in phase. So when you combine them, you're subtracting. And then when you combine that result with the resistor, which are 90 degrees out of phase, you've got to add them like you would do an X and Y component of a vector. You've got to do a Pythagorean theorem. All right. So that was our proof and kind of my summary. I guess I'm not trying to prove that equation, just trying to remind you of the proof we did. Then it's just a matter of plug and chug into here. We can put 150 and square it. We can take the effect of the inductor, which is a simple 78.5, and subtract off the 1,591 and square it. That's why I was saying again, I think you're seeing the biggest effect is right here. Even when it's combined in this weird mathematical way, the inductor is taking something off, but still that's going to be dramatically bigger than the resistor. So the overall opposition, which is called the impedance, and so the total opposition, when you put all of them together, the reactance of the inductor, the reactance of the capacitor, and the resistance of the resistor, what do you get? So taking the 78.5 and subtracting it, the 1,591, I guess you get that number, which I will now square, and add to 150 squared. And then finally take the square root of all of that. And I get 1,519 ohms. And all of these were in units of ohm. So I probably don't need to show you that you take an ohm and you square it and then take the square root, it's an ohm. So I think you're good with that one. But notice that this number is the effect of all of them. And it actually is a little bit smaller than just the capacitor by itself. Even though the resistor added more to it, it added it at right angle, so that didn't really add much. And the inductor actually took some away. Yeah. And so that's the overall. Now, maybe before I go any further, let me check these answers. This is 19. So we got a 78.5, a 1,590, good, a 1,520. Okay, good. Now, knowing that, this was really the main purpose, page 2, of going through all this mathematics and making sure you know how to find the overall opposition, that is the impedance. Because when you go to calculate the current, and this is what D is, so D, find the maximum current. So maximum current. And the reason we say maximum again, because it changes with time, is that you would then take the maximum voltage and divide it by that impedance. So coming back to my circuit, I think I wrote down 110 volts is the maximum. So 110 volts is the maximum. The impedance we just did, 1,519 ohms. So if I take 210 and divide it by that last answer, we're looking at a 0.138 amps. Remember, a volt over an ohm is an amp, or maybe 138 milliamps would then be the maximum current. And this is the more complicated and more interesting part of these AC circuits, is that because of the way the voltage is induced in the inductor because of a change, the currents that you have may not match up mathematically with the change in the current. And so your voltage maximum may occur at a different point in the cycle than when your current occurs at its maximum. Okay. And so there's this question for E. It says, what is the phase angle between the currents and the voltage? So in other words, if I were to do a graph, I'll call this the time axis, and the current looks something like this. And I deliberately did not put a vertical axis just to say, well, I can put that anywhere I want. How about I put it right here? Okay. So that means I would probably be describing the current as a sine function. I could have easily just put it here and described it as a cosine function, or put it here and described it as a minus sine function, or put it here and described it as a minus cosine function. So I can call time equal to 0 anywhere I want, because it keeps, changing all the way through infinite amount of time. We don't really have a beginning and end to this little circuit discussion. But I would say, okay, where is the voltage? And so maybe to make it stand out, I'll plot the voltage in red. But it would follow a sinusoidal pattern. It would be the same frequency, but the voltage peak may come earlier, may come late. And that's what these numbers would tell us. See, we know that the numbers here are dominated by the capacitor. So I would say that this circuit acts more like a capacitor than it does an inductor. Quite a bit more, as you can see. So because of that, the idea of the capacitor is the ice. The C for capacitor. What's nice about remembering the word ice is that this is saying the current comes before the EMF. And that kind of makes sense in a capacitor. Remember, you don't get a voltage on the capacitor until it gets some charge on it. So you have to have current first. See, it's the current that flows into the capacitor that has to come first before it'll build up charge on the capacitor. So some people like to remember the name ice. I kind of like that. But I prefer just going back to the basic physics and saying, well, the reason you get current first is you don't get a voltage until you get charge there. And you don't get charged until you get a flow. It would be like trying to make a lake in a dry desert. You might go, okay, hey, let's make a lake out here. So the first thing we have to do is build a channel. Okay, so we build a channel and then we turn on the water to flow through the channel. So what do you get first? Do you get the flow of the water or do you get the lake first? Well, clearly you have to have the flow first. So you have the current flowing in first. Once the flow goes on for a while, then you'll get the lake. You'll get the EMF. So current's got to come first. So again, if I was plotting current, then my voltage would have to peak a little bit later. And then same thing when I get negative current, my negative voltage and my 0 point would have to be a little later. Oops, and my drawing came out pretty poor. But hopefully it's enough here to get you to kind of see I'm trying to draw a voltage or an EMF here. I better do scripty that is a little bit behind. It's acting more like a capacitor. And of course, we had a calculation here that says the tangent of that phase angle is the difference between the inductor and the capacitor and then the resistor. So taking my calculator here, and I think the last time I used this, I was in radians. So why don't we go over to degrees, just so we can give an answer in degrees. But the reactance of my inductor was the 78.5. And the 1,519. And so there's the numerator, if you will. If I divide that by the resistance, and I believe we were talking about 150, yeah, I would get a negative 9.6. And that's got to be really close to negative 90 degrees. So inverse tangent of that number gives me a phase of negative 84 degrees. I wonder maybe if I should do radians. So let's see. Convert into radians, I'd go times pi and divide by 180. So negative 1.47 radians. Now, the negative is telling me that the voltage is behind the current. It's telling me the whole capacitor effect, the whole ice effect, the fact that you have to have current first before you get a lake. So to make a lake, you got to flow in first. You got to have current before you get voltage. So current is before. In fact, it's like I said, it's almost 90 degrees. So the peak of the voltage is just shy of the zero mark of the current. So we almost by the time we get our maximum voltage, we almost have zero current, but not quite. It's not 90 degrees, but it's pretty darn close. If it was a pure capacitor, then it would be 90 degrees. And so that was our argument that of the capacitor, that it would be a 90 degrees out of phase, and technically a negative 90 degrees. All right, between the current and the source. So let me just check my answer again. 19. Let's see, 19D, good, got that. And 19E, negative 84. It's 84.3. I got 84.1. So maybe other than some rounding, we agree there. Nice. All right. So there's our first impedance, our first overall reactance to it. All right. Let's move to the next one on the list. Actually, let me just out of curiosity, check the chat, see if anybody. Okay. Yeah. Yep. Yeah. Your classmates will definitely be looking at this, I think. So good. All right. So no new comments. I'll just keep going down your list, Chen, here. So let's see. Next one on your list was number 21. All right. So chapter 33, number 21. Oh, let me go back to my blue here. Put a timestamp on here. Okay. All right, so let's try 21. 21, probably not much different than this one. It's in the same section, so maybe we'll go a little quicker on this one. But it says in an RLC circuit, okay, consisting of a resistor of 150 ohms, so that's the same as the last problem, and a 21 microfarad capacitor, and a 460 millihenry inductor connected in series with an, give us an AC source that has a frequency of 60 hertz, and they say 120 volts. Now, they're not as clear as they should be. Are they giving me the maximum voltage, or are they giving me the RMS voltage? And because a wall plug in North America is 60 hertz and 120 RMS, I'm going to go with the idea that when they give me the 120, they were talking about the RMS. So let me go forward with that. We'll check that in the answer, but they could be more clear. But at the same time, maybe I'll take this as an opportunity. You should learn that. So in North America, which includes Canada and Mexico, United States, and some, but not all, of the Caribbean islands, an RMS of 120 volts and 60 hertz. But the rest of the world got most of its technology through its colonies of England, and so they copy Europe a lot of the times. Anyways, their RMS is 240 and 50 is the frequency. So that should be known. I think there's a few countries in Africa that might be under the US standard, but again, most of those African countries were colonies or imported their technology from England, and France, and Germany. And of course, England and the Dutch all had a big play over in the Asia area. Anyway, so there's some history there, and then that's how we have it. You can kind of see it in the roads too. Some people drive on the left, some drive on the right. I guess most on the right. It's just all the British and the British colonies that are on the left. Okay, but guessing that the 120 is the RMS, I'm going to go to A. What is the phase angle between the current and the applied voltage? And then B, which reaches its maximum earlier, the current or the voltage. So this is not only similar to the one we just did. It's actually a much shorter question. So it's got this same circuit, but it's only asking about the phase angle. So the tangent of the phase angle is the reactance of the inductor minus the reactance of the capacitor over the resistance. So why don't I fill those in? Let's see, the resistance is the easy one. That's 150. But the reactance of the inductor, that's the omega L. So that would be 2 times pi times 50 times 0.46. And we are looking about 144.5 for the reactance of the inductor. That doesn't seem like a very big number. So I'm going to think that the capacitor here is dominating. But let's do a number. 1 over omega C is the reactance of the capacitor. So 2 times pi times 21 microfarads. Oh, I've got the frequency. And I messed up here. I wanted the 60 up there. All right, I'll have to go back and fix that. All right, let me just check. I think I got this out of order, but there's the 2 pi 60. And then there's the 21 microfarads. Let me take the reciprocal of that. Oh, it's not what I expected. Okay. 126.3 ohms for the reactance of the capacitor. And for reactance of the inductor, just double check, 2 pi times 60, there's the frequency, times the 0.46. I made it a little bigger at 173.4. Okay. Now, this, as you can see from the numbers, is most affected, although they're all pretty close to the same, but it's most affected by the inductor. And the inductor is why we have the Eli. The L for the inductor, but the inductor is just the opposite. The voltage comes before the current. So we get a positive angle. So if we are making a plot of the current again, there's a current. The voltage would come before the current. So it's going to peak before it. And given these numbers, it's definitely before, but not much before, right? This is the inductor and the capacitor balance each other. And if they exactly balanced each other, they would be in phase. And so we're going to be a little early. But not by much. All right, and so let's find out what that number is. So we've got 173.4 minus 126.3. Yes, it's 47.1. And then I divide that by 150 and take the inverse tangent. Yeah, and we're only looking about 17 degrees early. So phi 17.4. Notice a positive. So definitely dominated by the inductor. Maybe dominated is too strong of a word, but more affected by the inductor than the capacitor, and even more than the resistor itself. Although by the time you put the effect of the inductor and capacitor would cancel each other, this is more affected by the resistor than the two of those when combined together. But anyways, I think that's the first part of this. What was this one again? Number 21. 21A says, which reaches its maximum, no, A. What is the phase angle between the current and applied voltage? Okay, so 17.4. And we already answered this, but we'll say it again here to put an answer down. It says, which reaches a maximum earlier? So since it was the Eli, the voltage is the earlier one. And so you can say something like the voltage leads the current. I guess you could also say the current lags the voltage, depending on how you want to phrase which one is leading or which one is lagging, which one is ahead and which one is behind. I mean, I guess they mean the same thing. See how your author does it here for 21. So 17.4, and they say here the voltage leads the current. All right, good. All right, next one on this list, number 24. And 151. All right, maybe this will be a good one to do before we head off on our break. You haven't done too many of your lists. We might have to go extra long, make sure we get them all in section 3. Or maybe we won't talk too much about the advanced stuff there. But good questions nonetheless, James. All right, so focusing on number 24. Let's see, 24 says what? 24. 24 says we have an AC source. Okay, so my AC source, I'll draw a little picture here, which has a V maximum of 150 volts and a frequency of 50 hertz. And it is connected between points A and D in the figure. Now, figure looks like this. Let's see, connected. So, okay, here is point A. And then they have a resistor, which they label as 40 ohms. And they have a point B. It then comes into an inductor. Inside the inductor, they label as C, and they give this as 185 microhenries. Then from C through a capacitor at D, which they list as 65 microfarads. And so they said that the AC source is connected between A and D, so it'd be something like that. Calculate the maximum voltages between A and B, all right? And then question B, between B and C, okay? And question C, C and D, and then D between B, and D. Okay. All right. Well, in all of those cases, in A, we should be able to get the voltage, since it's just a resistor, as current times the resistance. And in B, which says between B and C, so this is an inductor, we can get the voltage as current times the reactance of the inductor. And in C, we can get the voltage by saying it's the current times, let's see, C and D, the reactance of the capacitor. And then in D, it would be the voltage times the, and it looks like B and D. So B and D would involve the reactance. I don't know if I want to put Z for impedance because it's not the impedance of the whole circuit on D. So maybe I should just put, I'll do it this way for a moment. The reactance of the capacitor and the reactance of the inductor. The reason I wanted to write it that way is to show you that in all four cases, one of the factors we need is the overall current. So let me just do that. What is this current? And they do ask for maximums. So if I put M for maximum, I need maximum current to give me maximum voltage. So maximum current would be the maximum voltage of the whole circuit divided by the impedance of the whole circuit. Now, the maximum voltage, that was given as 150, and the impedance of the whole circuit is, like we were talking earlier, I guess it was back on 19, it's this crazy thing, right? It's the fact that we got to combine the reactance of all three elements, the inductor, the capacitor, and the resistor. The only tricky part is, even though they say in series, we don't add them like we would three resistors because they have this phase effect on each other. And the inductor and the capacitor, when we say we add them together, we really subtract them because they're fighting each other. They're out of phase. And the resistor is then, what we call 90 degrees out of phase. It would be like a y-axis compared to an x-axis. So we'd have to combine it with a Pythagorean's theorem. So with that in mind, this would be then a 40 squared plus, maybe this would be a good place to say, what is the reactance of the inductor and what is the reactance of the capacitor? Remember, this is omega L, and remember, this is 1 over omega C. Okay, so the reactance of the inductor is 2 times pi times the frequency. This problem has a frequency of 50. And then the inductor is 0.185. So this is a 58.1. Now for the capacitor, we go 2 times pi times 50 for the frequency, and then times the capacitor, which is 65 microfarads. Let me take the reciprocal of that, and 49.0. 49.0. So you can see that the inductor and the capacitor almost undo each other. Not quite. The inductor is a little bit stronger at this frequency. So at this frequency, I would say it acts more like an Eli. That is, we would have the voltage before the current. I don't know if that question's coming in later on. No, it doesn't look like it. So those were the other problems we just did. But let me get then this number. So the 58.1, but subtract off the 49.0 and square it. So there's not much effect here. 58.1 minus 49.0 only leaves me a 9.1. So that's what I was saying by saying the inductor and the capacitor almost cancel each other off. Most of the impedance is coming from the resistance, not from the reactance. But this is still a piece. So I'm going to see what this comes out to be, but I have a feeling It's not going to be much more than 40. But let's see. So we'll square that and add it to the 40 squared. And then take the square root. Because that'll be 41. So 41.0. So as I said, a little bit more, but really most of it is coming from the resistor. Inductor and the capacitor almost undo each other. All right, so if I take the 150 and divide it by that last answer, we're looking at a current of about 3.66 amps. So there's our current. Now, like I said, I needed all of that to go ahead and figure out the voltage across each of the individual elements, and then D, a combination of the two together. All right, so taking the current of 3.66 and multiplying it by the resistance of 40, we're talking about 146.4 volts. Now, for the inductor, it'd be the current 3.66 times the reactance, which we said is 58.1. And so it looks like 213 volts is the maximum there. The capacitor, 3.66 times the reactance, the capacitor was down here 49, 49.0 comes out to be 179 volts. And kind of the fun one to see here is D, because the reactance of these two together, they battle each other. So the reactance would be the difference between them, which we calculated earlier as 9.1. Maybe I'll do it again. So that's 9.1, and then times that current of 3.66. And so we're looking at 33. And it's kind of fun to see that the voltage on the two of them is never very big. Separately they are, but remember they're opposites. So they don't occur at the same time. It would be a mistake to add those two together. You would like to subtract them, and that's going to get you your 33. So one is in a positive voltage and the other one's in a negative voltage when that happens. All right, well, let me check the answers here. Number what, 24? So 146, good. They got 212, okay, good. 179, good. 33, good. Nice. And did they do? Yeah, and they did it basically the same way. So nice. All righty. Hey, well, it's a few minutes after 2, so why don't we call it break time here, and we'll come back and keep working on this list. Oh, let me cross out 24, and then we'll come back with 27. We'll do 27 and 41 and 42, and well, I won't read them all, but good break time. All right, guys, see you in a little bit.